a computational-based linear algebra is fairly simple because we can simply plugging in the numbers into the formula and get a desired outcome. For example, when we trying to solve a system of linear equation with Gaussian elimination or Cramer's rule, we just have to find out the coefficients of each unknown and then use the given equation or the given algorithm and we can get a desired outcome. However, it's not the case when we are approaching a higher level math, which is based on the proof, the rigorous deduction, and logic. For example, in this question, we have the following setup. Let T be a linear map on a finite dimensional vector space V such that the rank of T is the same as rank of T squared. Show that the image of T intersect with the kernel of T is the zero vector. So we do not have any direct formula for us to have a very simple one-step solutions, which is quite common in higher level math. But I encourage you to pause the video and think about it for the moment and try your best, and I will show you the solution. So at least what I can see is that, well, this is a very tricky question because we have a t square. Well, t square means the linear map composite with itself. It is not like a square of a number. It's not the same. So how do we approach this? Well, because T is a linear map on a finite dimensional space V, it does not mean that it is from V to the another vector space like W. It is to itself. So if it composites with itself, the domain and the codomain of this function out of this linear map is again a linear map from itself to itself, or if you know this notation, it is an element of the vector space of linear map from a mapping to itself. Okay, so how can we use this information that is given to us? Well, when we deal with this kind of problems involving transformation, I think the first thing we can think of is the dimension theorem. The dimension theorem stated if we have a linear map that is from V to W, then the dimension of V equals to the rank of T, or as we know, it is also the dimension of the image of T plus, I will write it as dimension of kernel. Well, you can also write it as the null of T. Well, this is your personal choice. So you can see that we have this element here and this right here. So we have to create this one and use this equality to link them together. Well, as we stated here, we can see t squared is nothing but the same as t in the sense that it is still mapped from V to V. So by the dimension theorem, the dimension of V also equals to the rank of T squared plus the dimension of kernel of T squared. Well, you can see how the given condition can be used. These two are the same, and these two are the same by the given condition right up here. So what does it mean? It means that the dimension of kernel of T is the same as the dimension of kernel of t squared. Well, how can this be helpful? I encourage you to pause the video for a few seconds to think about it. And this is what I have found. Well, as we know that the kernel of T is the subspace of V. Well, this is very obvious. We can just prove it using the definition of subspace. And the kernel of T squared, similarly, is also the subspace of V. These two are both vector space. So we can use the following fact, which I will not prove because the proof is tedious and somewhat obvious. If the dimension of V equals the dimension of W, if and only if V is isomorphic to W. Okay, you can prove it just by using the definition of dimension and what is in isomorphism. Sorry, I used the wrong word. Okay, so anyway, but this fact we do not have to assume that V and W are finite dimensional. But anyway, in this case, the V is finite dimensional. So since the kernel the dimension of kernel of T equals the dimension of kernel of T squared, we can see that kernel of T squared is isomorphic to kernel of T. Kernel of T is isomorphic to kernel of T squared. Okay, but how is this helpful? Right, if we just create a function, bijective linear map between the kernel of T and kernel of T squared, again, we can't see how this is relevant. But if we think about it a little bit more, these two sets isn't just two random simple sets that have a isomorphic structure. Indeed, how they are related. If we consider an element, for example, call it W, that is inside the kernel of T, by definition of kernel, we can see that the kernel the T of W equals to 0. Well, this is the definition of kernel, obviously. But if we take the function again, well, we also know that it is very obvious from the definition of linear map. T of 0 is 0 given that T is a linear map. So T of W is again 0. So W is inside the kernel of T squared. Well, this is helpful. Why? Because it means that the kernel of T squared is a subset of the kernel of T is the subset of kernel of T squared. Well, but also by this isomorphism, we can write it again like this. And with these two facts and some basic knowledge of set theory, we can see that the kernel of T is the same as kernel of T squared. Well, because these two sets are isomorphic, and also one of it is the subset of the other set. We can, even you forget your set theory course, what you learned in the course, you can kind of see from the structure of these two sets how they are relevant given the subset relation and isomorphic relation. Well, this is a very helpful fact, but let me reframe it again. So, how do we get to here? We start with these two linear transformation. And then, this is our first step. And then, we use the dimension theorem. And we get this result. Then, using this method of dimensionality, we conclude that the kernel of T is isomorphic to kernel of T squared. And by little kind of unobvious or obvious, depends on how you see that, fact that the kernel of T is the subset is a subset of kernels of T squared. And we come to this fact. Well, you might ask, it is not at all obvious for me to start from the very first step of the rank of T is rank of T squared to the step that kernel of T is the same set of kernel of T squared. It's not obvious at all for me. Well, it is. It is not obvious, to be honest. But how do we come to this step? It is not by checking the solutions. Well, if you're stuck at a problem for more than 2 hours, you can search online on step exchange. It's not a problem. But how do we come to this step? It's by trial and error. For example, when we see that there's a T square or T composite itself, we should have the sense that we should try to construct two equations based on the dimension theorem. It is a guess, it is a try, we can try multiple times. Sometimes we can get a result quite quickly. Sometimes we might stuck at a problem for 30 minutes, and once we searched it, it is fairly obvious for us. Well, it is how we learn from mathematics. It is by failing and failing again. It is very normal. So anyway, here is our result. We have shown that the kernel of T is the same as kernel of T squared. Well, do you remember what we have to show? We have to show that the kernel of T intercept, the image of T, is zero vector. Well, proving the intersection of two sets or any set is just a zero vector is not very obvious for us to how to show it directly, but we can try it by, you guess it, we can try it by contradiction. So suppose that V is not a zero vector and V is inside the set kernel of T intersect image of T. Well, we can then use the definition of kernels and image to write that the T of V is 0. And because V is also inside the image of T, there is W inside V such that T of W is equals to V. Right? This is the definition of image. So we have to use these two facts with the kernel of T is equal to T squared to try to reach to some kind of contradiction. So, well, you might ask, what can I do? I don't know. Well, how do I know? It's by trial and error. So this is what I see. Well, we have to use the fact that the kernel of T squared. So I have to create some kind of composition, right? But if I do this T of V, it is not quite useful, as I can see. It does not help us at all. So maybe we can do T of W. Then what is it? It is T of V, but T of V by 2, it is 0. Well, what does it mean? If we look at it clearly, or we write this one as T squared W. So W is inside the kernel of T squared. But what is kernel of T squared? Kernel of T squared is kernel of T by this fact. we have just proved. So, since kernel of W is inside the kernel of T of W is 0, right? It is also by the definition of kernel. But if you look at the number 3 again, what is T of W? T of W is V. So we start with what do we start with? We start with V is not 0, but we end up with V is 0. So what does it mean? V is 0. But V is arbitrary. V does not impose any kind of condition on the choice of V. So for any V that is inside the vector space V, we can get that. Because it does not give us any other choice for what can be inside the intersection of kernel of T and image of T. And that is how we solve this problem.